So in the lab, you found out that current has a direct relationship with field. More current means more electrons moving, and that creates more magnetic field. We also got an inverse relationship with distance, which makes sense because if you go farther away from an object, then it should have less field. Um, Thing to point out, because it's the only field that doesn't do this, this is the only field that's not an inverse square. Okay? When we did gravity, electricity, when we later do light, when we later do sound, they're all going to be inverse squares. And that's because those are all points of intensity. Imagine like a speaker. It spreads its sound out like a sphere that fills up the room. But with magnetic field, it's an inverse relationship because it actually doesn't have spherical symmetry, it has cylindrical symmetry. If you're imagining the current traveling to the right here, r is the radial distance, but it's the radial distance that's along a cylinder. So if you're wondering what's up, like why are all the other ones inverse squares? Well, that's because the square on the bottom of that relationship has to do with the area of a sphere, whereas the single in this equation, that has to do with the circumference of a circle. It's the difference between 3 dimensions and 2. All right, so let's go over what parts of this equation we need then. This equation says that there's a direct relationship with current and an inverse relationship with radial distance. That means when we go do this mathematically, B is going to be the magnetic field measured in Tesla. Mu is still permeability. So you should remember mu from when we did permeability of a solenoid was like the core of the solenoid. In this case, permeability is the permeability of the material that surrounds the wire. So a regular wire in our classroom, you would take permeability of air because air surrounds the wire. If you put the wire underwater, you would take permeability of water. If you buried that wire in the ground, like a electrical line running to your house, you would do permeability of the ground. Current is going to be measured in amperes, radial distance measured in meters. But since you're only going to have to do proportions and graphs with this relationship, right, what we can do is we can ignore the permeability in 2 pi when we deal with any sort of proportions questions. So let us see what some questions might look like. And I will have you help me out here. Okay. So using this equation, we're going to pretend, like when we do a proportions problem, pretend that mu and 2 pi are not there. If you double the current, that puts a 2 in the numerator, and it makes the magnetic field twice as big. So if I put more current going through this wire, then the field at point A would be larger. More electricity, more magnetism. So now I'm going to have you help me out here. What do you think would happen if I took point A and I moved it farther to the right? Would that cause the field to increase, decrease, or stay the same?
It's going to stay the same.
And why?
It's the same distance from the wire, no matter if it's moving left or right.
Exactly. And it's the same current. Like no, like I doesn't change, R doesn't change. Cool. So I can do that one. So moving along the wire doesn't change the field. How about this one? How do the magnitudes and directions of X and Y compare to each other? Let's start with the magnitude first. Which one has the stronger magnetic field, X or Y? If X is farther away, do you think it has more or less field?
Probably less.
Right? Because it's like farther away from the source. It's kind of
Yeah,
how things would be quieter if you were farther away from a speaker.
that makes sense.
Okay, how much less?
I heck is like calf?
Exactly. Because this isn't an inverse square. So if you double the distance, then it cuts in half the field. You don't have to worry about like squaring anything here. Okay, but now a harder one. So one of the funky things about magnetic field of a current carrying wire is it's a different shape than the other two fields we've already done. This is a field that's a circle in shape. So if you picture the field at X, it's kind of going around this as a cylinder in this direction. Y is going around in a cylinder in this direction. And since they're both on the same side of the wire, they're going to have the same direction of field as each other. Now, we're going to totally do the new right-hand rule in just a second, but a shortcut here. A shortcut is if you have two things on the same side of the wire, these will have the same direction of field. It's going to be a little funky to get this direction though. Technically, this is called the out of the page direction. We will get there. All right, how about we try like one more? What about how do the magnitudes of X and Y compare? How do the magnitudes of X and Y compare? They would just be the same because they're near the same wire, so they have the same current. They're the same distance away, so they have the same R. They're going to have the same size field. Maybe those are both, I don't know, 50 microtesla or something like that. But since they're on the opposite side of the wire, they have opposite direction of field. Okay, but let's talk about field direction. A funky thing about the straight current carrying wire electromagnet is it makes a closed loop of field, but it has no distinct north and south. So unlike the other two where we could just go, oh, it points from north to south, this one we're going to need to be a little bit more careful about. So this is a demo of what's called Ampere's law or Oersted law. Notice that when the current is off, all the compasses kind of point towards magnetic south because the north end of a compass is attracted to a south pole. But as soon as the current is turned on, they all form up a circle. In this case, that circle is all clockwise. So this is actually the same rule as the solenoid rule, that the current and magnetic field are always perpendicular to each other. Except we've switched what is going in a circle. With a solenoid, it was current is going in a circle, but this time magnetic field goes in a circle. The compasses are lined up in a circle. Last time, your field was pointed in the direction of your thumb. And this time we're going to make current, because current is the thing moving in a straight line, point in the direction of your thumb. So I'm going to show you a bunch of different examples of this. And if we start with this one, what I would do is I would take an object like a pen or a pencil, hold it in my hand and make a thumbs up. This is another thumbs up right hand rule. I want you to take your thumb, hold on to the material, and move your fingers until your fingers are pointed clockwise. So I'm going to line up this marker with the direction of the current. And in order to make my fingers turn clockwise, I have to point my thumb down. In order to do that, my thumb has to point down. That must mean that this direction, this current, is traveling this way, down into the piece of paper. You might notice that this one is a little trickier because you kind of have 3 dimensions going on here. You've got a circle going down in the X and Y plane, but you have a 3rd dimension. Your current is going into and out of the page. So I'm going to show you a few examples, and then I'm going to show you some notation tricks here. Okay, so here's one example. I'm going to grab my, grab the wire, the thing that represents the wire, grab that in your hand, make a thumbs up. I need to line up this with the wire. So I'm either going to have my thumb up or thumb down, and I'm going to choose based on the direction that the compasses are pointing. In this case, the compasses are pointed clockwise, and the only way to make my fingers point in the same direction as those compasses is to point my thumb downward. It's kind of like this. I know that the current is either going to go up or down. I don't know which, but I'm only choosing between two directions here. In order to make my fingers curl clockwise on my right hand, I needed to point my thumb down. So this must be going down is the direction of conventional current.
Wherever your thumb goes is the current direction.
That's it. So thumb is going to go in the current direction. All right. Let's do another one. So in this case, I'm either going to point my thumb down towards the paper or out of the paper, but I'm going to do that until my fingers line up with the direction of the magnetic field. So in this case, when the current is on, the magnetic field lined up like this. It's not a perfect circle, but there's actually a really good explanation for that. Because there's the magnetic field of the current, but also the magnetic field of the Earth. So if you're wondering why is it not a perfect circle, well, it's because it's still reacting to the Earth as well. Okay. So I'm going to hold this marker in my hand, make a thumbs up, and I need my fingers to be going counterclockwise. When my fingers are going counterclockwise, I can see that this marker is pointed out of the page towards me. So I would say this current is going this way. And you can kind of match it up to this hand here on the right. The thumb is going up, so the fingers are going counterclockwise. Okay, but we're going to step this up because a funny direction thing happens. We know that for straight current carrying wires, they're going to be perpendicular. So we're going to point your thumb in the direction of current, and your fingers will naturally curl in the direction that the magnetic field goes. And since this is a right hand rule, it's got to be with your right hand. Okay, I don't know if you need that. Okay, well, I would pay attention to this part just because this rule is hard to picture. This particular rule. The high five slap rule makes sense to me. This one is harder. Right. So what I want you to do is point your thumb in the direction a conventional current is flowing, and your fingers are going to end up curling in the direction the compasses would line up. Okay. So let us grab our object that we're going to do right hand rule with. Current is pointed down. So I'm going to turn my hand upside down. Conventional current points down. And if I look at my fingers, I see that they're going in the clockwise direction. So I would draw the magnetic field like this. My fingers are curling clockwise around that wire. So if I wanted something like the direction of magnetic field at point A, a compass at point A is going to point in the direction of magnetic field. This compass points left. Ooh, and let's check to see if it's still perpendicular. The current is down, and my magnetic field at point A was left. Down and left are perpendicular to each other, so I know I'm good. I did that right. So this fun thing happens though. We're going to take this and rotate it. Once we take it and rotate it till it's exactly 90 degrees, this trickier thing happens. Okay? So let's say I point my thumb to the right and I'm curling my fingers around it. When I do that, my fingers are curling, but they're in a direction that's hard to draw, right? On the top of the wire, the fingers are going towards you. On the bottom of the wire, your fingers are going away from you. You're trying to draw a three-dimensional curl on a two-dimensional paper. So here's what we do with this. Right? Imagine your hand is here. Where your fingers are, we're going to call that direction into the page. So I've actually seen people do this on tests before. It's very silly. Into the page direction is going to be a symbol of an X. So I've seen people on their fingernails of their right hand put like little X's. That direction is going to be called into the page. The opposite of into the page is out of the page. So that must mean above the wire, we're getting our field going in the out of the page direction. The reason that's hard to picture is the Z direction is fundamentally a third different direction. Remember, left and right are X, up and down are Y, but going towards you or away from you is Z. It's a third dimension, so it's hard to draw on a two-dimensional piece of paper. So for this, there's two new symbols you need to learn: the out of the page symbol and the into the page symbol. You can technically use these two symbols for any vector. So for instance, if I were throwing you a ball and it was going towards you, that ball would have a velocity in the positive Z direction. And we would represent that by a dot. If you threw a ball to me and it was going away from you, you could represent its velocity vector as an X. Dot and X are going to be our two new symbols for our third dimension that can't be fit easily on a piece of paper. One thing I do like about the fact that you guys all have open notes tests this year is there's only a limited number of things that are going to go in the Z direction. So if you drew them all out in your notes, then you wouldn't have to like sit there with your hand and go like clockwise, counterclockwise, into, out of. So why those symbols are the way they are. I want you to imagine that right behind your iPad screen, I want you to imagine there's like a little tiny person shooting an arrow vector at you. Maybe you like angered them for some reason, and now they're gonna get you with an arrow. When that arrow goes through the screen, the first thing you would see is you'd see a point. That's because it's going out of the screen towards you, the reader. And that's why it's a dot symbol. But for every action, there's an equal and opposite reaction. Let's say you're going to fire back at them. So you grab your bow and arrow and you notch it backwards and you fire a traditional arrow complete with feathers and all at your iPad screen. The last thing you would see as that arrow punctured the screen is you'd see a little X, the hatch mark from the two little feathers on the back. That's actually why that symbol is the way it is. Dot symbol is going to mean a vector that's going towards you. X symbol is a vector that's going away from you. So let's say I make the dots and X's. Let's say I make the dots and X's currents. So I've got current, and this is a dot symbol. So it's going out of the page towards you. You're still going to keep your hand in the same shape, but I want you to point your thumb directly at your face. And from that view, I can see that my fingers are making a circle, so I know it's a circle. But I see that my fingers are going in the counterclockwise direction. If I had this as a current going towards me, I would be looking down and seeing compasses going in a circle around it. Okay. Similarly, let's rotate this around. So it's still same exact hand position, but now I want you to point your thumb away from you, like this.
Oh, so we do that.
And then it goes the opposite way. So still making a circle, but now it goes clockwise. Now, totally a thing you can do since we're doing open notes tests this year. By all means, if you want to write down this picture so you don't have to do this right hand rule, you could do that. I do know on later physics that you can't do that. But you have open notes tests, so please take advantage of this. Note that anytime the current is out of the page, that's the dot symbol, that means your field vectors, your compasses would make a circle. No distinct north and south pole, but it would make a circle going in the counterclockwise direction. If you have current into the page, you would point your thumb away from you, which is really inconvenient to do. I see my fingers are curling clockwise. And so instead of memorizing these, you can write them down now and have them for your test.
So would that be the direction of the current?
So red in this case is going to be direction of current, and blue is direction of field.
Okay.
So we're going to do just one more thing with it, because you'll notice if you go to problem 16, 17, 18 on your homework, it does this with currents going into and out of the page, but also with currents going right and left. So one thing I like about this is if I make the current go to the right, I take my pen, I put it in my hand, I've got the right hand, I point my thumb so that the current goes to the right. Then I would see that where my fingernails are, those become X's. The opposite side is dots. And every other problem that's in this orientation, you can get the answer by simply rotating it. So let's say I needed up instead of right. I could rotate this 90 degrees and see dots on the left and X's on the right. I would take my hand exactly in the same position every time and rotate it to match the problem. So if I look at like problem 17, I would just rotate my hand 90 degrees or 180 or 260, and it would still give the same orientation. So you could take this picture, rotate it to match the one in the homework, and figure out where the into and out of the page fields are. But what I'm thinking at this point is I put in 4 Nearpod questions, but we are just about out of time. So I think instead of doing the Nearpod questions right now, when I see you on Tuesday, then we are going to go over the homework for the weekend. We'll play a quizzes to review all the stuff from this week, and then we'll do the last 2 topics in this unit. So let's just go over and make sure you've got the things you need for this week. This week, we've done 3 types of magnets. We've done ferromagnets. Well, let's find it. We've done ferromagnets, which is like your bar magnets. Fields point from north to south. Domains point from south to north. Made of big chunks of iron full of domains. We did solenoid electromagnets, which is coils of wire. You'd put your fingers in the direction of the coils, and your thumb would point north. We know that your solenoid electromagnet would depend on its core, its current, its compression, and the number of coils. And And your last type of magnet would just be your straight current carrying wire. The wires in your house do this type of field. The type of field that depends on the current and how far you are from it. For that, we point our thumb in the direction of current and our fingers curl in the direction compasses would line up. So that was the whole thing we did this week. To practice it, you have homework 8.1 that's due Saturday. Experiment 8A was the one that did like ferromagnets on one half and solenoids on the other. And the one you should already have turned in, please already have turned in before you leave, experiment 8B. The one we just did about current carrying wires. Wires, but spelled right. Yay!